Okay, tonight the objectives here are learn about switches, switching protocols, routers, and routing protocols. Up till now, we've done a lot of theory. Tonight we're kind of getting a little bit into, well, a lot into actually, what the hardware does for us, what the routers do for us, what the routing protocols, and I want to try to do demos with those. Instead of just saying, okay, this is what happens, I'm going to try to show and using Packet Tracer what actually does happen with these protocols, what they do for us, what they allow to happen, how they allow us to have a more flexible network. So about routers or switches and switching protocol, and about routers and routing protocols. I'm going to pause here. Back to this. We're going to look at some of these things, some of the protocols that we have in switches and in routers. And if you go the ICND route, this is kind of a jump start on it. A lot of these things, the things that we're going to talk about, and some of the demos that I'm going to show you I use in the ICND1 class and ICND2 classes. Module A, switching, about the problems with complex layer 2 topologies. If we want to create some redundancy, we have an issue. I want to show that. I want to show the difference between what happens at layer 3 and do that first, looping, and layer 2. And what can we do about each of these things, and how switching protocols are used to prevent looping and congestion, and how VLANs can partition layer 2 networks. So we're going to have VLANs, virtual local area networks, where we're going to break the switch up into broadcast domains. Kind of a cool concept. We'll look at that. I can talk about it all day long and shake your head and yeah, maybe we can see what some of those things do. So the first one here, simple switched network, we don't really have any issues. And let me bring this over. If we simple, this is the one that I'm going to do one of the demos with, but a simple switched network, if we got some switches in here, what they're talking about is kind of an extended star, or maybe a little tree here. I keep losing my switch. That we could do something like, and we're going to use crossover cables to go to switch, like to like is a crossover cable. Something like this arrangement, no problem. And we could even, well, let's just go from here to here, and from here to here. These amber lights represent a protocol called spanning tree, which is going to allow us to create loops. These things are okay because they're distinct paths. There's no duplicate path for any of these guys. If I don't do that, I'm going to cause an issue. But since spanning tree is running on these things, actually I want to do a different one, and I'll turn it off. Actually, I can go ahead and turn it off. Go around here and let this one work. We're just going to make this little loop here. One of these should turn green and the other one should stay amber, orange, whatever color that really is. Because what we're done here is create a loop, and we have the spanning tree protocol running by default. This is Cisco simulator, but running by default on the Cisco devices. It takes about a minute, 50 seconds. You can see it sit there and flashed and flashed and flashed. And now I've got one green one and one not green one. So one of them is up, the other one isn't. What I want to do now to show you what happens, and this is if we don't have that protocol running, and then we'll turn it back on. Actually, I'll do my other one because I've got it already set up with the workstations on it. What I wanted to show you on this one though is at layer 2, we already have something in the protocol, in the IP protocol, called a time to live that prevents an endless loop. And in this one, and I tried it just to be sure it would work, trace route, and this goes to a network that really doesn't exist. So we go here, we have our hops going back and forth, and you can see it goes 1.2 and 2.1. That's the two routers. So it's bouncing back and forth between the routers, but after it gets to the 30 hops, which is the TTL, it's done. We don't have to worry about it anymore. It gets bounced back and forth, and that's an artificial thing that I set up with this. I did default routes, which says that sends everything here, and this one said send everything here, since I really don't have a 4.1. This one is a 2.1 network. 1.1 and 1.2, I think, are the two addresses of these. But if we have an IP network, then it'll bounce back and forth, bounce around on the internet until its time to live, its TTL, has expired. And then this simulator didn't send me back a message, and you actually do get an ICMP message back that says that the packet is expired en route. But what I want to do right now is to open a different one. And I think it was this one. I'll save the changes. This has got a whole bunch of different ones around here, but this still isn't got the one that I want. But yeah, we'll build one. We'll build one that we want. What I want to do is just a little simple one here. Let me put another switch in here, and we'll build the same type of looping that we had in the other one, except a little bit simpler here. So it's going to do that. I want to put a couple of computers in here so that I can generate some traffic. Sometimes on the simulator I have to generate traffic, and sometimes it doesn't really care. But this is, I think, kind of similar to what the one shows in the book. So while that's setting up, let me put some IP addresses on this guy. 8.1.1 and 192.168.1.2. So now spanning tree works. You can see one of these is turned off. I don't really have a loop. So in order to make this thing fail, I need to go in here and turn that protocol off. Span tree VLAN 1. I'm probably going to have to turn it off on all of them. Notice that it changed. That the port changed, the one that was down. So it's still trying to break up the loop. And we still got this one that's still trying to make it work. And let's see if we can shut it down completely. Okay, now I don't have any. I've got a loop. I've got a layer 2 loop in this thing. And not a whole lot's happening because I don't have any traffic on it yet. If I go in here and I forgot 192.1.1 ping 192.168.1.1. Let's just ping the this thing. You notice the time to live, time here is increasing, and this thing. Let's try to ping the 1.2. I just wanted to generate a whole bunch of traffic on that thing. and it slowed down. I'm going to get a timeout. And now I got a time here, 32 bytes, 185 milliseconds, time to live 128, timed out. So it becomes inconsistent. We've set up a loop, and in layer 2, we don't have any way to break that loop up. And on this thing, kind of the indicator is these turn dark green. But what happens is I send this out, and well, let me do it on the image. If I go back in here and turn it back on, and turn spanning tree back on, it all fixes itself pretty quickly. So spanning tree protocol is the protocol that protects us from loops, inadvertent loops, or on-purpose loops in layer 2. Now if I turn this back on, and it's working, we can tell it's working because the amber lights, it's going to take a while. Story, true story. I used to work with a guy who had set up a network. We were in Roanoke, Virginia. He'd set up a network in Chicago. He was a big Cisco guy. Got called in for consulting, and he was teaching some classes with us. He had set up or worked on, I don't know if he personally did, but I know he had worked on the network, maybe as a project manager of a big organization in Chicago. And everything was working fine. They elected not to use the spanning tree protocol. He got a panic call one day. Network's down. Entire network was down. So flew him to Chicago. He said he walked into the NOC, the Network Operations Center, and moved one wire and brought the network back into operation because somebody had moved a wire, one wire, and created a loop. This is just a simulator thing on this one, I think. So now we should be able to go in here and ping. Normally we get a 1 millisecond time here, time to live 128, 32 bytes, and all that stuff. But our times are back to what we would expect, and then less than 1 millisecond. So spanning tree protocol is the one that allows us, and you can see here, to have a moderately complex network with some redundant paths, redundant physical paths. And if one of these ports goes down, it will, and we can do that, it will, let's see if it makes me a liar, then create a new path. It'll go into a new negotiation, and we'll see if this, and again, takes 50 seconds. There is a faster one of these, but negotiation, let's see if this one actually opens this port right here up, which it should, as I stall and stall and stall. Sometimes we go away and come back, and I won't do anything. Let's look at some of the slides, and we'll come back and look at this thing. We're just going to drag it over here and let it run. And as I did that, I'll drag it back. Didn't have time to do anything. This one is now up, so it automatically brought the port up from a blocking state and said, okay, you can use me now. Takes a little bit of time, but you don't have to go out and try to troubleshoot the entire network as to what happened to the system. So let's connect this guy back. And you notice this one goes back down because it kind of has the idea that it's not going to be the path anymore. So the spanning tree protocol demonstration and so on, I never know whether to try to do demos before or demos after, but in here, simple switch network, no real problem as long as we don't have any layer 2 loops at it. It's going to use the MAC addresses to find the nodes on down the line. And when we had the tree, the extended tree, it would record the MAC addresses of everything that's on that port, obviously, so that it knows where to send those to. And we can have more than one MAC address on a port. But in that case, a link failure is going to result in a network failure. If one of those wires failed, port failed, somebody unplugged it, as in the case with my friend's experience, we have a network failure, a network issue. Redundant links can help that situation, but as you saw, redundant links without some help result in redundant failures. Because what happens, and on this thing, as we go around and around and around the world, and let me see if I can make any kind of sense out of this. But when we go out of here, if I'm trying to go, if I ping workstation B, whatever it is, the frame comes into here and workstation A's MAC address gets put on the port that it's connected to. It doesn't know where workstation B is. We're going there, so it floods out the packet, the ping, whatever we're doing, to here and to here, because it doesn't know where to go. Okay, so these guys don't know where they are. But he thinks that A is here, and he thinks that A is here, because, hey, we know the source MAC address of these things, because that's the first one that's in the frame, is the source MAC address. So, hey, now we've got A on a whole lot of different places. This guy doesn't know where B is, so he floods it out. We got A here. He doesn't know where it is, so he floods it out. And we've got A here. So now we get to switch 4. Switch 4 doesn't know where it is, so he floods it in all directions. What's happening is we're getting the MAC address. The MAC address table is going to have a lot of flip-flopping going on, and these frames just keep going around and around and around in the switch, and you saw that. Yeah, it slows things down, maybe shuts things down, but the layer 2 protocol, multiple paths, will crash the network. And in fact, told you the story, that is a true story. It did crash that network. A layer 2 topology, no real checks on being able to fix those situations. And here is the header information. We had the preamble, 7 bytes. It's just a series of 1s and 0s for synchronization. Start a frame delimiter. We're starting the frame. We have the destination MAC address, the source MAC address, the type, 2 bytes the type here. And as we saw yesterday when we looked at that in Wireshark, the type is either going to be IPv4 or IPv6 here. The data payload, 42 to 400, 1500 bytes. And then the CRC, the cyclical redundancy check, that is just to check to see if the frame was damaged en route. If you go down there and look at the Wi-Fi, just out of curiosity, the payload for the frame is a packet, but it has 3 MAC addresses. It's got the destination MAC address, the source MAC address, and then it's going to have the MAC address of the router, because the wireless got to go to the router before it goes to the destination. So a little bit different header, but same impact for the wireless and the wired. If we don't have some mechanism to break up these loops, we're going to be in trouble. We're going to bring down the network. And spanning tree is the protocol that does that. It's an election process, and here spanning tree stops layer 2 loops. And I'm looking around here, you can tell I got too much stuff open, but what I want to do, if I can get to my folder, I have a little demo, got lots of little demos, where I can hopefully, if I can find my little demo, look at how this spanning tree business works. I guess if I just searched on it. Maybe it will find it for me, or not. I know what'll find it. There it is, spanning tree. This is a little, so how do we figure out which one of these ports to block in their blocking state? We're going to look at the states in a minute and the states that it goes through. So this is the, and this says bridges, bridge, switch. When you see bridges, think switch. Switch is a multi-port bridge. So we have this looping situation set up, similar to what we showed here earlier, what I showed in the how it didn't work. So I boot up all the bridges or switches, think that they are the root bridge, a new term here. The topology of this thing, we had a block port, one of them that was shut down. The topologist thing is that we're going to elect one bridge as the root bridge so that all of the other switches find a loop-free path to the root bridge. And then we will determine which port to shut down in order to create, maintain that loop-free topology. So in this thing, they're all going to say that they are the root bridge. And what really happens here, these things, and we have these really big MAC addresses, 1, 2, and 3. We have also in here a bridge ID, and it starts out with 32768. That is the priority, and we can control the priority. We can't control the MAC address. What is going to happen here is the one with the lowest MAC address is going to wind up being our root. So this guy sends a BPDU, another, we talked about PDUs, protocol data units, with the don't some people fight back situation, but these are bridge protocol data units. And this is the reason that that company that I was telling you about didn't want to have spanning tree, because it sends these things back and forth all the time to try to create, maintain the loop-free topology. So in this one, the C is root because we sent, they communicated with each other. C sent its BPDU up here. It's 2. This one's 1. He's still root. This was 3, 2. Okay, the other guy is root. And we will keep going with this. And 1 is going to now send his information to everybody else. And they'll do the comparisons here. And we're going to wind up electing bridge A, the lowest MAC address, as the root bridge, the one that everybody's going to make a path to. And if you think about which switch in our network is going to have the lowest MAC address, probably going to be the oldest switch. So may not be the best thing, but it's one of those things that you need to know, because we can manage the priority over here, the 32768, the default. We can set those, and when you set them, it's one of those, okay, I'm going to set it high so it'll become the root. Now you want to set it low so it becomes the root, the one with the lowest. In switches, when they do elections, typically the lowest is going to win, and in routers, typically the highest is going to win. So we have elected the root bridge. Now we've got to determine our loop-free topology in this thing, because that's the whole objective of all this thing. And down here, all links between the bridges have the same speed, 100 meg. It's going to be a cost, and we're going to have cost to determine the path that we're going to take. So in this thing, a root port, we're going to have a cost of 19, 19, and 19. So obviously to get to the root bridge, we're going to go that route. I know you're going to watch me draw again. So we have a cost of 19 because we're assuming that these are 100 megabits, and that's just a number, the cost of these things. So this one, root bridge, This is going to be the root port. The root port goes to the root bridge, and all of the ports on here are going to be called designated ports. So there'll be designated ports. The root port goes to the root bridge. In here, one of these, either this one or this one, is going to have to be put into blocking state. We're not going to go this way because the cost would be 38. We're going to go this way to the root bridge. So we now have to determine, actually I messed that up, didn't I? That's not true. I lied. The eraser's not working tonight. Yeah, it is. One of these ports is going to have to go into the blocking state. We're going to shut it down. Shutdown is permanent, or not permanent. It's a manual proper action. So the system's just going to hold down the transmission of data across one of these ports. So when we go here, let's see, the containing the designated ports referred to 3 segments, 1, 2, and 3. We got all of that. Segment 1, 2, and 3 designated ports on the root bridge. Path cost, we got that. Anyhow, we could go through this thing. What happens is, again, the lowest, the designated port here, designated port is going to go toward the root bridge. So this is going to be a designated port. Will go towards the root when we do those things. And this one here says a root port, designated port goes to a root port in all cases, and they can kind of switch. And these are forwarding blocked. The one with the lowest MAC address is going to stay in forwarding mode. So again, lowest everything is going to do that. This is the image out of your book, and it's like, okay, we have the root switch inactive here. Yeah, maybe not. The direct would depend upon the costs to get through here. Both of these are probably not going to go. Only one of the ports is actually going to go into blocking mode. So spanning tree, it is the IEEE 802.1d standard. Operates the data link layer. Hopefully the demo at least implied that. Prevents traffic loops, and hopefully the demo showed that it is used when we want to have multiple paths, multiple physical paths from one location to the other in case we have a failure someplace. Calculates the path, avoiding potential loops. It uses the spanning tree protocol to calculate that loop-free topology in the network. Artificially blocking links, completing the loop. It actually puts them in, and it does block, and the state is a blocking state with these things. The STP information transmitted between switches uses the BPDUs, the bridge protocol data units. 3 steps. We're going to select a root bridge based upon the bridge ID. The bridge ID, if all things are equal, if they have the default 32768, then the root bridge is going to be the one with the lowest MAC address. If we want to force the root bridge, we can lower the priority. Since the bridge priority, the priority on the left, the 32768, is in the most significant digit portion of the priority, it's going to have the most influence on the number itself. Where it's going to be, what's going to happen to it. So, examine the possible paths between the network bridge and the root bridge. So the possible paths, we're going to look at cost, and it's going to take the lowest cost. And the cost is going to be a function of the data rate. The 100 meg actually is 19 is the one that's still used. There's 2 standards. They change as you might expect because back in the day, before the gigabit ports, different cost scheme than today with gigabit ports, and as we're going to 10 gigabit ports, it's going to change again. We're still using the one that includes the hundreds and the gigs, and I think that the gig is a cost of 4. The 100 obviously is a cost of 19. Disables links not part of the shortest path, and that is a bad term here. I'm going to change it right here before your eyes. I'm going to say it blocks. Blocks links not part of the shortest path. It blocks a port, puts it in a blocking state, and the one when I showed where I took the cable away, it's in blocking state so the spanning tree can negotiate and say, oh, I need to bring that one up because I need to create this path. The path that I had isn't there anymore. One of the BPDUs, the Bridge Protocol Data Units, that happens is a topology change. When something like that happens, sends a topology change announcement, and then it goes and recalculates the path. And again, it takes, obviously, in the networking world, 50 seconds, almost a minute, is an eternity. And there are other ways to do that. We have a rapid spanning tree protocol which works much, much quicker. But now that we've gone through all of my hopefully not extremely confusing explanation, we have the bridge priority 0 to 65,535. So that's it's 2 bytes in here, and then we have the MAC address, which is 6 bytes, the 48-bit hexadecimal number that is unique to every layer 2 interface when we do those things. Spanning tree does have frequent communications, and again, that's why the company in Chicago didn't want to do it, because it's got a lot of traffic, little bitty packets, but lots of traffic, lots of them. BPDU is a unit. The Bridge Protocol Data Unit is the unit that is used for the communications. It uses the bridge ID, which is the priority with the MAC address, in order to determine which is the root bridge. And the root bridge, again, is going to be the one with the lowest whatever. If we want to force one of them, and you may, because, again, do you want the root bridge to be your least capable bridge? And if you use the defaults, that's what it's going to be, because it's going to wind up being the oldest one in the system. Determines the loop bridge, a loop-free path from every switch to the root bridge. We're going to do this, and even though there's switches, we still say root bridge, and that is actually the term that's used, not root switch, but root bridge. In the beginning, bridges were what were used to separate layer 2 segments so that we could have less traffic, hopefully fewer collisions. And when they incorporated that technology into switches, but switches do this in hardware, bridges do it in software, every port became a bridge port. So, and sometimes switches are called multi-port bridges when we do those things. So this one, kind of the topology that we saw, we have all of these, the priorities on each of these 32.768, the MAC address 000A, this one's 000, and we can just look at the beginning and say, okay, this guy's going to be the root bridge. All of its ports on the root bridge are going to be in a forwarding state. That's one of the ways that you can see what's going on with it. The path to the root bridge is called a root port. The state of these are not the state, they're going to be in forwarding. They are called designated ports when we get there. And you notice we have a cost of 4. All of these are gigabit. If this was play a what if game here, if this were 100 meg, it had a cost of 19, it wouldn't go directly. It would go this way because the cost would be less. So it really is dictated by the cost. And this one got put into blocking state. But the BPDU activity still continues, so that if something happens to one of these others, it goes down. it can communicate, and the protocol will allow it or force it or bring it up so that it now completes the path the new path that we would have in this thing. So STP, Spanning Tree Protocol's job is to find all the links in the network and shut down any redundant ones, preventing network loops from occurring. It achieves this by electing a root bridge that will have all the ports and forwarding, and will also act as a point of reference for all other devices within the STP domain. All the other devices within that domain are going to find a loop-free path to the root bridge. This is just thrown in the block port. The process that these ports go through down from the bottom up. Disabled is administratively down, and in the Cisco world we go in and give it a shutdown command, say don't do anything. Administratively down, nothing's going to happen. So the first thing that happens is they're going to be in blocking, and over here say blocking is going to be for 20 seconds. Blocking, it's going to receive BPDUs, only going to receive BPDUs. Then it's going to go into listening state, where it's going to build the topology. This is when we're actually figuring out the topology. Learning state, it's going to accept MAC addresses. It's going to build its MAC address table. And then after that, it's going to go into forwarding state, where it actually forwards the frames. If it doesn't go in forwarding state, it's going to go back to blocking state if it's not one of the ones that's going to be brought up. Disabled, shutdown. Disabled is not one that Spanning Tree does. It's thrown in there because it shuts down the port, but it is manually down, not with the protocol itself. Let's try to do this one last one. Link aggregation here. Spanning Tree stops all of our blocking, or all of our loops here, but there are situations where we might want to have a higher data rate port, and we do have a topology that allows that. And I'm going to have to find it. Find the let's see, what am I looking for? I have one here. I will find it. Probably up the top, huh? We've got a lot of labs in here. Ether channel, that's what I want. What we can do, without making you go through all of the configurations, if I set this thing up with Spanning Tree, two of these would be down, and one of these would be up. One, two, well, we got three of them here. But you notice all three of them are up. This is called link aggregation, and the protocol that we use here, the LACP, Link Aggregation Control Protocol, is the one that they talk about, as well as PAGP, which is a Cisco proprietary protocol. The way we can do this, actually we could, let's see if we can do that real quick here before the break. And let's hook these things up, and I'm going to say the dotted lines are crossover cables, crossover like to like. I'll say that because those are little things that we sometimes allow to escape. What we do here, if we set this thing up, Actually, we said that we could do that. Let's see if we can make it faster. Let's see. Spanning tree. And we're going to do mode. Rapid. There is one called rapid. When we do that, and I want to do that one. Rapid per VLAN spanning tree. But again, we set this thing up. We got all these connections here, but I only got one of them going back and forth. If I want to make this faster, I can go in here and create a channel group, and we'll see if I can do this. If I can get this range fast Ethernet 0/1 to 3. Let's see. Now it's not channel group. Yeah, it is channel group. But channel group, and then on these things I'm going to assign it a number. And I think that's all that I can do here. Now I have to give it a mode. Mode, and we'll do the LACP. And the LACP, we can make this, let's make them both desirable. Up, down, when we do these things. And let's do switch port mode. I think I need to do that. So I hadn't done anything except make a mess yet, have I? So spanning tree is blocking these things, and we get the messages, and we get BPDUs on the non-trunk. So let's go to the interface. And I'm doing interface range. I'm doing all of them at once. If I can find the dash. 3. Yeah, I hate it when it does that. Group 1. And what was it? Mode. And we're going to do desirable. And if it worked, and this is again a simulator, and sometimes it will and sometimes it won't. Oh yeah, it did. So it turned all of them green. So now I have a much higher speed virtual connection between the two switches. NIC teaming, I think, is the Microsoft word. If you have a very busy server and you want to have more than the 1 gig or whatever the NIC is, you can aggregate links on a switch and aggregate NICs on the device and have a higher speed connection. It's going to share each of the individual, in this case 100 meg links when we look at it. If we go in here and do if I can do it, show interface, yeah, let's see, show interface PL, maybe that's PL1, maybe switch port PL1, or maybe I'll figure it out while we're on the break. I just want to try to show you that it is a higher data rate than we had on those things. So couple of things that we can do. STP stop the loop. Sometimes we want a higher speed. Link aggregation provides that. There are two types of link aggregation. This says LACP, which is the standard. LACP stands for Link Aggregation Control Protocol. Static teaming. We can use statics if we want. Microsoft recommend that you use one of the protocols, and you got to use one or the other. You can either use the LACP, the standard, or you can use the Cisco proprietary one. Let me get that other one. The next thing we're going to look at is VLAN, Virtual Local Area Networks. But let's go ahead and take a break and come back. Let's come back at about 10 minutes past the hour, and we'll do VLANs, and then after that we'll get into routers for a few minutes. Questions or comments? so that the instructor could get to the resources that they needed, and the students couldn't get to the places where they shouldn't be. But the image here, and what they've started doing, and it probably makes more sense, is instead of calling them numbers, we call it the red VLAN, the blue VLAN, and the green VLAN. And all of the ports that are in the green VLAN, all of those computers can talk to each other. Can't talk to anybody else unless we have a router, because broadcast domain, we're talking an IP network, an IP subnet, in order to group those together. When all the interfaces in a switch are in one broadcast domain, when we start up, they're all in the same domain. They're all in the same VLAN, which is VLAN 1. That's created automatically for these things. We want to group them together to create broadcast domains. The hosts in a VLAN can be present in different physical segments. Can be in different locations. Or in the case that I gave, we could have, well, they were in different physical locations in different rooms. And whichever room you went to, you would go to the instructor machine. It would be on the instructor VLAN. You could get the resources for what you needed. We have to have routers in order to allow the different VLANs to talk to each other. Should make sense because they're different IP networks. And there the ports are assigned are static and dynamic. Dynamic is really cool, sounds really cool, much harder to configure, and you have to have special equipment to do that. But in a dynamic VLAN, the computer gets plugged in and gets automatically assigned to a VLAN based upon its MAC address. The static VLAN is the one that I want to try to show some of here. This is a copy of the one over here, so I can mess this one up and then we can go back to the other one if I need to. I've got two different IP subnets here, 192.168.3 network and the 192.168.2 network down here. It's not configured correctly right now because I want to go through some steps to hopefully show what happens with these things. So on the 3.3 here, let's go to this guy, and I've got a 3.5 and a 3.6 and over here a 3.4. So let's see if we can ping 192.168.3.4, and the answer is no. We're going to work on that problem here in a minute. 3.4 is on this other switch over here. We've got some other configuration, another term to learn so that we can send the data across it. But now let's talk about 3.5 and 3.6. Let's try 3.5. Hey, I'm in great shape. Same IP. Yeah, we would think that would work. Let's try 3.6. And I don't get anything. And the reason I don't get anything is its port, which is port 3, hasn't been assigned to the proper VLAN yet. Static VLAN assignments here. If I go in and do a show VLAN, and I know I'm using some of the configurations that probably you don't need to know how to do these things, but the result is what I want you to see. But we have the VLAN 1, the default VLAN's got everything on it. It also has 03, the port that my guy is on. So I had the two network, 23 and 24 on it. They should be okay, I think. 1 and 2 is on VLAN 3. When you do VLANs, I got the .2 and the .3. I've always been a fan of whatever the subnet ID is. Hey, let's make that the network name or the VLAN name, because it becomes a lot easier to get everything associated together when you do that. So I'm going to go to interface. I'm going to go to configure mode first. Interface, fast Ethernet 03, which is the one I want to do. And the way I put it on there is this: I go switch port. I'm going to do something here. I want to say it's an access port. We're going to have two types of port: an access port that we plug computers, printers, in devices into. And we're going to have another one called a trunk port, which isn't configured yet, that sends information from one switch to the other on all of the VLANs. So we'll just go in here, switch port, access, VLAN 3. And now, if I get back to my device, I wonder what I wanted to do, was it? This was the guy we were using, right? 3.5, and now I can communicate with 3.5. And these guys down here, 2.5 to 2.3, ping 192.168.2.5, and it can do 2.5. The other one I think is 2.4. And on the other switch, we still can't get there. Pretty frustrating, right? I want to look at the other slide first, but VLANs, yep, we can do that. Actually, the other thing that I guess that we could do here that I want to try to do here is to put this in simulation mode and ping the broadcast address. Ping 192.168.3.255 should ping all of those guys, and I should be able to go into simulation mode here. Goes into the switch, goes out all of the ports on its VLAN. You notice it did not go out the ports on the other VLAN because we have created broadcast domains with this thing. So broadcast domain, and the objective of that is so, yep, we really do create broadcast domains, and it's not just that we plug a bunch of switches in or a bunch of devices in on different IP subnets and they can't talk to each other. They couldn't talk to each other anyway, even if we didn't create the VLANs. What we do with them is minimize the amount of broadcast traffic that goes to every one of the other devices, and Microsoft has a lot of broadcast traffic. The other concept that we need to, and I talked about trunk ports, is VLAN trunking. And this is supposed to show, represent, we have the blue VLAN and the red VLAN. So here all the red VLAN can talk to the red VLAN, the blue VLAN can talk to the blue VLAN, and they don't talk to each other. Their broadcasts don't go to each other that we just saw on the switch that we just did. The trunk port up here has got both red and blue on it, which means that it can have information from all of the VLANs on it. It's called a trunk port, a trunking protocol, 802.1q, which tags the frames as they leave the switch with the VLAN number. When it gets to the other switch, it takes that VLAN number off and puts it on the correct ports for that VLAN, because you saw in the configuration it knows which ports are on which VLANs. So this one, connecting multiple switches, each containing multiple VLANs, communication path is needed for each VLAN between the switches. VTP, which I'll demonstrate in a second, VLAN trunking protocol, advertises configuration. Trunking is a mechanism that enables the traffic from multiple VLANs to coexist on the same physical interface. Boy, that's a mouthful. What that means is that we can have traffic from all of the VLANs on the trunk port, and as you saw in the arrangement that I have right now, it's not working. And it's not working because I'll have a trunk port. The ports that are connecting the two switches together are access ports, and they're in VLAN 1, the native VLAN, the default VLAN that we have on these things. A VLAN trunk acts as a point-to-point link for carrying traffic between the two switch interfaces in a single interface, and then when trunking is used, VLAN IDs are added to the frame headers to transfer the information. It acts as a I think it's a 4-byte shim that gets put in the middle of the frame, and when it gets to the other side it gets taken out, because if you sent one of those tagged frames to a computer, it wouldn't accept it because it would be a non-standard frame when we do that. Well, we can look at one here, the frame, the VLAN header. We have a tag protocol, tag information, two types of VLAN tagging, and I'm going to mention it because it's in the book. The first one is the 802.1q, which is the one that's used today, which is the one that Cisco uses today. The other one, the lower picture down there with all the nice colors on it, is called the Inter-Switch Link header structure, the ISL trunking protocol. It's a Cisco proprietary. It's an old Cisco proprietary. It doesn't even show up on the Cisco switches today. So what I want to do, and I'll do VTP and mention what native VLAN is, and then the default VLAN we looked at. The default VLAN is VLAN 1. It's there. It doesn't go away. It is we can take ports off of it, as you've seen with it. I just added a port to this VLAN. But what we want to be able to do is to communicate with all of our .3 guys together and all of our .2 guys together. And the way we do that is to configure a trunk port between these two devices. And I'm waiting here to see gig 01. So what I would do is go into interface gig 0/1 and just give a switch port mode trunk command. Change state to, now I've got to go to the other side. I'm going to go. It should negotiate, but I'm going to go ahead and give it a manual also. Switch port mode trunk. And if you want to know if you got one, you're going to show the interface trunk, and yeah, we have one. And when we have it, mode is on. It tells us what our encapsulation protocol is, 802.1q. It's trunking and native VLAN. Native VLAN is a concept that goes back to what if data comes in to the switch from something that doesn't tag it. Oh, let's say a hub. If it comes in from a hub, it's not going to be tagged. So where's it going to go? It's going to go to this thing called the native VLAN. The native VLAN takes any untagged traffic, or any untagged traffic goes to the native VLAN. Stalled a little bit. We're up here. So now let's see if we can ping this 3.4 guy over here, which we couldn't do before. 3.4, and now we're in business because we have this trunk port enabled. So we can, and well, let's try the 255 and see if it goes there. Ping 192.168.3.255. And then we'll go to simulation mode here. And it's going over. Looks like we're in business here. So our broadcast domain now goes to both switches. And notice nothing goes to the .2 network because it's a separate broadcast domain. We do, in fact, create broadcast domains. The other thing it talked about, I want to be sure it's running, is VTP, the VLAN trunking protocol, and this is its status. Its mode is a server, which means I can make VLANs on it. It has a domain, so all of the switches that are in that domain are going to be talking to each other. So let's show let's make a VLAN that doesn't exist. 500.105. Let's create VLAN 600. And to create a VLAN 600. And we made it. And we'll name it name NetPlus. Now then, what the VTP, the VLAN trunking protocol, is supposed to do is to create that VLAN on all of the switches that are in that domain. And I didn't create it on this one, but here is the NetPlus VLAN. So it got created here. No ports on it, no ports on the other one. We can't do that, but we can maintain a consistent set of VLANs by using the VLAN trunking protocol. If we make it on one of the switches, it then gets propagated to the rest of the switches that are in a domain. And typically, hopefully, I guess, that all of our switches are going to be in our domain. The next topic is PoE, Power over Ethernet. These is the 802.3 AF standard. What this means is that we have Power over Ethernet or PoE switch, and we have devices, phones, IP phones, that we plug directly into the switch, and the power is provided by the switch. The first time I ever saw this, I said, golly, that sounds like a great idea, but what if I accidentally plug a non-powered device into it? If you do that, it checks to be sure that it's a powered device before it sends power across the Ethernet cable. So the amount of power down there, 15.4 for standard devices, 25.5 for the newer PoE Plus with the 802.3 AT standard. Two specific devices, the PSC, the power sourcing equipment, and the PD, the power devices, obviously are the parts of it. So the standard here, we're going to send power across the Ethernet cables. These work great. What do you want to use them for? Maybe for cameras, for surveillance cameras. You don't have to run power out to the cameras. You just run the powered Ethernet cable. Wireless access points. Up in the overhead, you don't have any power there. You get your Ethernet cable there from your PoE switch with your PoE device, and you've got a wireless access point. Cisco phones or IP phones are the biggest users of them because they go on a lot of desks. In a lot of cases, they didn't put in an extra outlet for the phone. So we just plug the phone in, or actually plug the phone into the switch. The phone gets its power from the switch, and then we plug the computer into the phone, which is actually a little 3-port switch inside of it. So the power over Ethernet, and this is some PoE power over Ethernet adapters. Here, just found a picture, or actually this is out of the book. The PoE adapters, special type of switches that provide power. One of the considerations to be aware of is how much power your switch now needs, because how much power is it going to be sending out. First, determine whether the node is PoE capable, and then if it is, it sends it to power. If it's not, it doesn't send it to power. It just treats it as a standard switch port. In order to go on to the internet. So we're going to do routing tables. I forgot to start the recording again. The common routing protocols, and then network address translation are the topics that we have here. So routing tables, in them, let me get rid of some of these packet tracers here and bring one up, and we'll look at a routing table. They've got a picture of one. I'll save that one. But we can look at some actual real routing tables with actual real routing protocols. It says network address, network mask, gateway, interface, and then metric. And those are things that we have on these things. First of all, let's see if we can do a simple one. I think I've got a RIP in here. RIP is one of the simplest routing protocols that we have. We can use it on some moderately complex networks. What Cisco, when we talk about the web interface, yes, they have one. Cisco, what you're typically going to have is we can do a workstation here, and we have a console cable that we go from the RS-232 port to the console port. And that's the way we would actually do the configuration. Packet Tracer kind of bypasses that by giving us this little CLI command line interface option here. And the reason I use it is I can make the font bigger. Hopefully it's a little bit easier to read. So if we show the IP route here, we have some routes here. The R's here said RIP. That's a routing protocol. It's shared information. We have the destination here, 192.168.1.0/24, 255.255.255.0. When we look at this thing, we have the network address, the network mask. The next thing is via 172.16.1.1. That's what's called the next hop address. That would be the gateway. That's the next interface it's going to be sent to. And over here it says serial 030. That's the interface it's going to go out of on this router in order to get to this IP address. The other thing it said it had was the metric, and it's also got this thing here, 120 is called an administrative distance. That's how trustworthy the route is. The metric here, 1, is hop count, and the hop count is how many routers away. We have here a 2 and here a 3. How many routers away is the individual or the next, that particular network when we look at that. So a routing protocol, a routing table. This is in fact a routing table for RIP. Here C's mean that they are directly connected. It says so right here is directly connected, serial 030. And L here, you notice, has got a 32-bit mask. What that says is that this is the host ID. This is not a network, even though they say it's a network with a 32-bit mask to 255.255.255.255 means that it is a host on these things. And we have the C's and the L's, and if you ever do Cisco, the codes are right up at the top of the routing table. So we have routing tables that have that information in it, and it has a lot of information in it. We'll go back to it. It's sharing information with all of its RIP buddies here. So we have routes to a whole lot of different locations. We can use these dynamic routing protocols, again RIP being one of the simplest ones. EIGRPO, SPF, we'll look at some of them. Their metrics are going to be a little bit different. They're going to be a lot different actually. But how we get from point A to point B. And on this one, we don't have, in some cases we may have equal kind of costs here. Let's look at this guy here. If we have in here if we have more than one path that's equal cost, it has both of them, and it will send data across both of these. So it will share the path, share the bandwidth to get from one to the other. RIP is one of those protocols that doesn't care about how fast anything is. All it cares about is how many hops away it is. If we had a 56K that was 1 hop and a 10 gig that was 2 hops, it will use the 56K. It's not a very sophisticated routing protocol. So we have that information in the routing tables. Local route entries in these things, the subnet, if we were to do our own route, we could do that, a static route. The command would be IP route, whatever the network is, and then the subnet mask. Actually, let me see if I can do that loop. That's how I made that loop. And we talked about, and we have talked about, and they have shown the 0.0.0, and that is the default route. But in this one, it's got static routes in it. Again, the way I made it loop was to send it someplace that didn't exist. Show IP route, and we have down here 0.0.0/0. That means it's got a 0.0.0 via 192.168.1.2, which is going to be the next hop. So if when I write that command, It's IP route, the next hop, or IP route, the destination. Well, if we could go ahead and just do one. IP route, and we'll go to some place that doesn't exist, 192.168.100.0 network 255. We have to have the subnet mask. And unfortunately, it shows with the CIDR up here, but we can't use CIDR in the IPv4 configuration. So the next thing here, the question mark, the forwarding router's IP address. What's the next hop address? And let's say it's 192.168.1.2. And then if I want to give a distance, if I want to put a metric on it, I can. I'm not going to do that. So now I have a route 2. Yeah, I won't do that. A route 2. Static route here to the 192.168.100 network via 192.168.1.2. So when we do routes, we have to have the information there. If you do static routes, if you write them, if we go from here to here, and this was the 100 over here, you gotta write the static route back. They're not as efficient to maintain. They are more efficient in bandwidth because they don't require any. They don't have any information sharing that's set up with them to go from one to the other. This is the one I think is in your book. It has the default as the gateway. The default is 0.0.0.0 with a 0.0.0.0 subnet mask, and this the 10.10.0 45/24 link 2 flags. This is obviously not a Cisco route table. This is another location. The other place that you can have a route table is in your very own computer. And we can go in here and use the command route print, and I have routes here. Down here I have some IPv6 active routes for the IPv6 route table. Up here a little bit easier to see the IPv4 route table. Let me be sure this is for the this is for the active Ethernet interface. There's some other stuff around on this machine, virtual interfaces that sometimes show up with these things. But I have a destination 0.0.0 with a mask 0.0.0. The gateway 192.168.1.1. Golly, that's my default gateway. The interface 192.168.1.27. That's this guy's IP address. The metric 25, and then we have 127 network on link, which means it's on that interface. 127.0.0.1 on down the line. We have 169.254, and the 169.254s we talked about last night are ones that we don't really want to see. That means that we're trying to get a DHCP address when we can't get to the DHCP server. This one shows up here because it's what's called an alternative address, that if I can't get one, then it's going to give me this address. 192.168.1.0, the interface 1.27 to get to all of these things. So we have in our computers, we have a route table also that we can look at. And this says remote routes, and this is the remote routes. How do we get to the remote routes? How do we get to those particular locations? Static versus dynamic. Static, you saw we have to configure it ourselves manually, IP route command in Cisco. You can put routes into your computer if you want to. Not really something you probably want to do. But static versus dynamic. Dynamic, the routing protocols where all of the RIP routers talk to each other, all of the EIGRP routers talk to each other, and all of the OSPF routers talk to each other. Protocols are like languages. They don't talk, they don't understand each other, so they don't talk to each other. The next one down there is interior and exterior protocols. There is one exterior gateway routing protocol that is used right now, and that's called BGP, Border Gateway Protocol. It's used to create the route tables for the internet. The interior routing protocols are going to be said to be under a single administrative authority. Single administrative authority would be like us, would be our network. LeaderQuest would be a single network authority. They would use interior routing protocols, interior protocols. Interior gateway protocols are typically what they're going to be called. Multiple protocols on a router? Absolutely. We can have multiple protocols running on a router. We can have RIP and EIGRP and OSPF, all of them. It will maintain the routes for all the protocols, but it's only going to show us the one that has the best, what's called administrative distance. And the administrative distances are over here. And if I go back to, actually, let me get one of the other protocols up here to show you some of the different administrative distances that we can kind of swap back and forth. I forgot which one has got a lot of routers in it. Yeah, this one's got a lot of routers in it, and it's got version 4 and version 6 on it. Lots of different areas. But if we go into it and use and this is loading adjacency OSPF adjacencies. When you get these, you say, okay, the routing protocols are talking. The routing protocol is talking. So all the OSPF routers are talking to each other. Show IP route, but they don't have any routes here yet. It's going to take a couple minutes, I guess. I thought it said it had an adjacency. Let's see if one of these other guys is getting anything. It takes a few seconds for these. We got loading, and this one says it's done. And it still only has the directly connected ones. It's still working up, and you know, it takes a little bit of time for these things to get their routes. And I know. It doesn't have IPv4 routing on it, so we could show. You can say IPv6 routes. So we have those. The O's here are OSPF. It shows the vias and all that, and we can see that we talked about the FE80s. You can see those, and let me open up an IPv4 one here, or try to. So let's do a different routing protocol. A B C D E. EIGRP. It says, I think maybe this one does have both of them on it. So if you do a show IP route and nothing happens and you have adjacencies, yeah, this one. Show IP route here. The D's here are the EIGRP ones, but so we have to get to the 10.20 network with a 24-bit mask. The administrative distance is 90. If I had OSPF and this running on it, the EIGRP is going to be more trusted. And you can see its metric is an outrageous number when we do this thing. But the next hop, the VIA and the serial interfaces are all the same. So each of them is going to have a different administrative distance. How trustworthy is it? How should I use it? Which one should I use first? As well as a different cost or different metrics to use to these things. And how hard is it to add one of these things? We just add it to the routing protocol, and it starts sharing the information. This is not a real complex network here, but if you look at it, it's got 1, 2, 3, 4, 5 routers. What if you had to write static routes? So we'd have to go from here, we'd have to write a route to this network, a route to this network, a route to this network, to this network, this one, this one, this one. And then on each of these routers, we got to write a route back to get to this guy. So the dynamic routing protocols, except in very small networks, probably something that we're going to want to use. If we are, go back to this thing, if we're the end device, if we only got one way in or one way out, like to your ISP from home or from your company, all you need is a static default route, because we send everything to the ISP and say, okay, you figure it out. You get everything on the internet for us, because that's what we're paying you for. So distance vector versus link state protocols. RIP is a distance vector protocol, hop count. How far in what direction. The other ones are what are called link states, and they say, okay, it's the state of the links. But what we have in these things, and this is the EIGRP, good. What we have are topology tables in it. Okay, EIGRP topology, which keeps track of the other, what the other routers tell it. It only shows the best in the route table. But you notice here we have two here, are two successors, and those are successful, but we have a topology table which is going to keep track of the topology of our network in these things. OSPF does the same thing. Not always the easiest thing to look at and say, oh yeah, that makes sense. Look at and say, oh yeah, that may not make a lot of sense. But distance vector and link state protocols. The distance vector protocol that we use is RIP. An actual link state protocol is OSPF. And EIGRP is called a hybrid protocol. It uses both of them. And if you look at that administrative distance table over on the right, EIGRP is going to be the preferred protocol if it's available at all over all of the other ones when we do those. We'll look at a couple of other things here. We don't have that much left in the lecture here tonight. So let's go ahead and take a break here. I say that, let me be sure, yeah, we're in good shape, I think. Let's take a break and come back at 10 minutes past the hour. Questions or comments? And I'll get you, Michael. We have a couple of more concepts, routing concepts to talk about, routing configurations to talk about. The first here, split horizon. And what split horizon says is that a router won't send a route back the interface that it got it from. What that's for is a route goes down, for instance, and we haven't updated all of the routing protocols. We're not in convergence yet, and then B or C wants some information. Let me go to the next slide here. Let's say that we have all these guys updating, and C says, yes, I got your update, and added 1 and 2. So he added 1. He sent 1 and 2 to this guy here. So he has networks 1 and 2. It has a path to them in the route table. Let's say network 1 goes down, and before, or actually it gets advertised to be as an invalid route. But then C updates B with the route that it has for the 1 network. And B says, hey, I'm in great shape. I can get to 1, even though it's down. And it can't, because the later update overrode it. What Split Horizon says is that B sent the route to 1 to C. C can't send that route back to B. Split Horizon down here. And down here it says, sending info about C router to A from B, sending info about C router to B from A. That's not going to happen because it got the information about C from B. It can't send it back. So you can't tell a router back the routes that it told you, is essentially what that's saying. Autonomous system here, we're talking about BGP, Border Gateway Protocol, the protocol of the internet. So a transit autonomous system connects multiple other networks and serves as an open conduit for traffic between them. A multi-homed autonomous system to multiple other networks, but doesn't carry external traffic. This goes on and on and on and on and on. What are we talking about here in the stub autonomous system? What we're talking about here is autonomous system numbers, and these are numbers that are assigned. I think IANA assigns these, and this is the way that the routers share information. If we configured it, and this is one that I found someplace, the BGP on these things, and you can see the configurations that take place. Whereas in EIGRP and OSPF, they automatically found their neighbors. We have to manually configure these things as autonomous systems in this instance. But show IP BGP, the network, and then the next hop, the network that's available, the network, the IP routes. This is in the BGP, but if we do a show IP route, B stands for the BGP 10, and then we have our administrative distance here, and then the cost, because they're going to be connected to each other when they do those things. It's a little bit of a different configuration. You can see it here, router BGP, neighbor 172.16.0.1. This guy over here, autonomous system 1. Go back to the slide here. Multi-homed autonomous system to multiple other networks, but doesn't carry external traffic. It just uses multiple connections for redundancy or load balancing. So we can have multiples for this, and BGP can be an internal gateway protocol if you want. It's much slower than the other ones, and it is more difficult to configure. A stub autonomous system connects to only one other autonomous system. And if we go to, I guess I go back to my guy has a stub. A stub is an end device. So these are both stub autonomous systems. They connect to one other one. This one connects to multiple autonomous systems, and they share the routes. They share them relatively slowly. It's kind of like a great big huge rip. It's slow to converge, and you expect it to be slow to converge, because if it started doing routing updates every time something changed on the internet, then a router went up or down, then we would be in a constant state of flux and as to which routes worked and which routes didn't work. But neighbors here that we have, when we manually configure them, EBG external border gateway protocol is what is being used here. IBGP, internal border gateway protocol, if we routed between the routers within the autonomous system, we would use the internal gateway routing protocol when we do those. Next concept is this thing called first hop redundancy protocol. What it does is creates a virtual router in here, and it allows us to have redundancy so that if one route goes down, first hop being our default gateway, then we can keep going. This route, both of these routers have it configured, and I've got actually two different groups here, but that doesn't really matter. I want to take this guy here, and I have done this just to see and see if we can do a trace route to the 1.3, which is this interface here, and I did a trace route to this server up here, the 172.16.2.100. First hop redundancy says that if I go in here, if this thing goes down, and this is, I think, gig 00, if this, I better check, gig 00, if it goes down, I can still keep going. I'm going to do a quick and dirty down on this thing. I can still keep going, but I'm now going to go through this other interface over here. So let's try the trace route again. So now it goes to 2.1. So when this interface went down, redundancy, first hop, my default gateway, and I have in the middle here an IP address for a virtual interface, the virtual router. And the virtual router also has a virtual MAC address, which is really handy because it gets put in the ARP table. You send it to it. It then controls which of the physical router interfaces that the information goes from one to the other. And if I do this again and go back and say wake up, it goes back to the 1.3. So it goes back to, and that's part of the configuration, it goes back to this interface. First hop redundancy protocol. This one uses the Cisco protocol, HSRP, Hot Standby Routing Protocol. There is a VRRP, Virtual Routing Redundancy Protocol, which is an open standard. But we have a virtual router here with an IP address and a MAC address. MAC address is a big deal to me because MAC address is how we actually get there. If we just changed from one IP address to the other, then we've got to wait for ARP to find the new MAC address for the default gateway. Since the virtual interface has a MAC address, there's no delay there, and you saw there wasn't really a whole lot of delay in that thing. So what we have here is a virtual IP, the virtual router. It's going to have an IP address, and then we assign the interfaces to this virtual IP address, and we control which one of the interfaces it's going to use, which one's going to be active. We're going to have an active and a standby. Obviously, the standby takes over when the active goes down, so we don't have a single point of failure at our default gateway in this case. The next one, and I think this is the last conceptual thing, is address translation, NAT, network address translation. And I have a demo for that, I think. I had them kind of lined up so that I use the right one. I have too many of these things. And one worked for the other. What NAT is going to do is to allow us to use our private IP addresses inside of our network, and then be able to translate it to an address on the outside. And I thought I had another one in here that I actually had two of them, but probably not. We'll figure it out. Which one is in that demo? Yeah, we're going to do this one. So what we do is we're going to have a source NAT and a destination NAT. And both of these are kind of set up here. The destination NAT is over here. The NAT process, I have the steps over here. Label the interfaces. We're going to label the interfaces as either inside or outside, so we know we're going from inside out or outside in sort of arrangement. Write an access control list. Here we go with access control list again, because we specify which IP addresses are going to be able to be NATed, and then we turn NAT on. This is the steps for PAT, port address translation, which is we use a single IP address, the IP address on the interface, in order to do that. Let me look and see, and we can swap back and forth on these things. I don't know which one is configured on this one, but we will see. This one has a pool which has different addresses that it's going to use. It's going to use the .5 to the .7, something very, very small, in order to go from one location to the other. I want to go ahead and show the NAT table, and then I'll turn this thing off, and you can see that it doesn't work. It doesn't work unless we do NAT when we do these things. And so the address we're going to here is 117.45.23.1, which is on the outside of our network. Ping. See, and I never can remember that address. I don't know why I used it. 117.45.20.23.1. And with any luck here, say wake up device, timed out. That's never a good sign, you know. Okay, so we did get there in the last two. Sometimes it takes these things a little bit longer to wake up, and then we can show IP NAT translations, and we have our inside local, which is the private IP address 192.168.1.2 got translated to the .5 address. And we have the port numbers here. And remember from last night, the port number, or the port number in conjunction with the IP address, is going to give us a socket that we can connect to. This one over here has a destination NAT, and we can NAT to the inside. Just maybe if we can show run here. So that we have an IP, and we have IP NAT inside, and then the IP NAT outside, and IP NAT inside. I've NATed the inside address, the 2.2 and port 80, which is the web address to that. And you would want a destination NAT and a static NAT, that is a static NAT that goes to a specific IP address. These guys over here went to a pool. Whatever address, the next address is available is the one that they're going to be assigned. This goes to, we want to go to a specific place, so we're going to do a static NAT to go to a web page back here. And the way we would get there is to go to our outside address there, which is 117.45.23.1. 117.45.23.1. I hope I got that right. Yep. And this is what the Cisco page looks like. So we have NATed. We can go back and forth on these things. The other thing that we can do, port address translation, and let me go in here and see if I can, and I can't because I've got stuff in here. NAT translations, and let's see if we can make those go away. I don't remember where it is. Erase IP NAT. I have to get rid of those before I can make NAT go away. But anyhow, for port address translation, we use the single IP address like you and I do. And what happens is we use the single IP address but different port numbers to go out onto the internet. Therefore, we have a unique socket, and it keeps track of those in the NAT address table with the translations, just like the one where we use the pool, the different addresses, so that we can use those up, and we don't. That means that we don't have to have as many public addresses as we have private addresses, because when they get back, then they give the address up. And here are the types: 1 to 1, the NAT table where we have the individual addresses, and they can be dynamic. We can do static. You saw the static or the dynamic, but we can use them out of a pool, or we could assign each of the private addresses a public address. The easiest way, obviously, is a pool, because what's going to happen is that once whoever goes to the internet comes back, gets done with that session, then they're going to give back the address. The next person can use it. We also have this capability, it's called overload, where we can, if we run out of addresses, we can go into this one-to-many down here, the PAT, the port address translation, where it shows that the NAT table here, let's see, one-to-many, yeah, goes to a lot of addresses. I want, yeah, one-to-many. One to many, yeah, one to many. This goes backwards here on these things, I think. But anyhow, one to many, that we do port address translation. In here, whichever direction we're going, it's nice of them that they used. And this one works both ways. What this one is showing is that the subnet, the outside interface is going to be 10.10.10.11 here. So this is on the 10.10.10.0 network, which is a private. That's why I say it's nice of them to use a private on both sides here. But each of these things would be translated to the public address, each of the privates, but they would have unique port numbers in order to identify that session, and in order to identify that session, that socket. I'll get there in a second, but to identify that particular socket number. And that we had source NAT, SNAT, source NAT, where when we go out we get NATed, and destination NAT, so that we're going to NAT to a specific IP address inside our private network. Maybe a web server that you're running inside. We actually did that for a while, so that you came up to the public IP address and it got translated to the private IP address to get to the web page. Not necessarily a great idea. When we talk about security, we're going to talk about DMZs. That's a better place to put your web server. You really don't want anybody inside your private network if you can avoid it at all. But an internal server may be there. You may have access control lists that only a few users can get to that one from the outside. Different sorts of ways that we could restrict access, but you really want to be careful about letting individuals into your private network. And then PAT, port address translation, this is exactly the one they showed over there, one to many. We have a whole bunch of internal addresses here from 192, whatever, says port 5100, port 5999. We're going to use multiple IP addresses internally and allow them to NAT, PAT, port address translation, to a single IP address, and they will be assigned unique ports. The unique ports will create the sockets, which will allow us to create the NAT table. So, time to do the fun part. You can say, oh goody, we're about